Now, in one of my previous videos that was called The Geometric Structure of Atoms Using the Golden Ratio, we looked at the possibility that atoms generate either a dodecahedral shape or an icosahedral shape along with their stellations. Now, in this video, we'll start to test this theory to see if it stands up. According to our previous video, a carbon atom can be seen as generating forces in the shape of a stellated dodecahedron or an icosahedron. To briefly explain what we're talking about, start here with our little black dodecahedron. But now let's add the stellations to turn it into a stellated dodecahedron. So here we have our stellated dodecahedron. But now if we then connect all the points of the stellations, we have an icosahedron. So here we now have our 20-sided icosahedron. So as you can see, we can use this process to go from the dodecahedron to the stellated dodecahedron and then to the icosahedron. Now, this is not the traditional way of looking at polyhedral duality, but I do believe that it is the more accurate way of looking at it. If you want to know more about polyhedral duality, there are a number of good videos about it on YouTube if you do a search. So how do we get to a Buckminsterfullerene? If a single carbon atom is indeed a stellated dodecahedron or an icosahedron, how do we arrange these into the shape of a Buckminsterfullerene, considering the fact that electron orbitals overlap? So here we have a cluster of 12 interlocking dodecahedrons. Now keep in mind that from this point forward, the shapes that we're going to talk about do not represent atoms. But what we are going to spend a little bit of time talking about first is the logical progression of polyhedral shapes that will get us to the shape of the Buckminsterfullerene. So with the 12 dodecahedrons that we have here, let's now add the stellations. So here we have 12 interlocked stellated dodecahedrons. If we now connect all of the points of the stellations, we arrive at a familiar shape. The shape that we then get is the pentarchus dodecahedron, which is made up of 60 equilateral triangles. Now when it comes to polyhedral duality, the dual of the pentarchus dodecahedron is the truncated icosahedron, or the buckyball, which is the general shape of the Buckminsterfullerene. So let's take a brief look at the polyhedral duality of the pentarchus dodecahedron. If we put a white dot in the center of every triangle, we get to the shape of the truncated icosahedron or buckyball. You can see here the shape of a pentagon as well as the shape of a hexagon. And if you joined all the dots, you would get the shape of a truncated icosahedron or buckyball. This is polyhedral duality. So now here we have two shapes, the pentarchus dodecahedron on the left and the stellated dodecahedron on the right. Now the little stellated dodecahedron represents the carbon atom. So what we want to do now is use the pentarchus dodecahedron as the platform to build our Buckminsterfullerene, which is made up of 60 carbon atoms. Now if a carbon atom is a stellated dodecahedron or an icosahedron, what we first need to do is start with a small dodecahedron and figure out the best way to cut it in half and then put that half onto the surface of our pentarchus dodecahedron. Now on this model here, you can see that process. Firstly, starting with the dodecahedron, which has been cut in half and placed precisely in the center of one of the equilateral triangles on the pentarchus dodecahedron. Then we add the stellations, and finally we enclose that shape to make the icosahedron. Now this process places our carbon atom at the centre of the triangular faces of the Pentarchus dodecahedron, and that is where it really needs to be in order to build our Buckminsterfullerene. So now we're faced with the huge task of doing this 60 times, while at the same time allowing for the overlap of the electron orbitals. So what would 60 interlocked stellated dodecahedrons look like? Well, following this pattern, so this is what 60 interlocked stellated dodecahedrons look like. As you can see, it's an incredibly beautiful geometric shape, with each stellated dodecahedron equally spaced over the surface of the Pentarchus dodecahedron. We can now see the shape of pentagons as well as the shape of hexagons. So here is a close-up of the shape of the pentagon. This is a close-up of the shape of the hexagon. So now what we need to do to get to the shape of the more familiar looking Buckminsterfullerene, what we need to do is connect all the points of our 60 stellated dodecahedrons so that we then have 60 interlocked icosahedrons. Now this is the shape that we get, the true geometric shape of the Buckminsterfullerene. At this point we need to think four-dimensionally and think of each little icosahedron spinning around like a little gyrosphere. Are you visualizing what we would be looking at? If you are, then you would see the crystal structure of the Buckminsterfullerene, which you can easily do a search on Google. Just search crystal structure of Buckminsterfullerene, and that's the shape you'll see. Does this prove that the geometric structure of a carbon atom is a stellated dodecahedron or an icosahedron? Perhaps. At any rate, it is at least plausible, but no doubt more testing of this theory needs to take place. So until next time, let's keep asking questions.